So I'm showing here n equals 5, the n equals 5 bicentric Poncelet family, a family of these blue pentagons interscribed between an outer black circle and an inner brown caustic. Now, to obtain the appropriate radius for the brown caustic that closes n equals 5 Poncelet, you solve something called Fuss's, F-U-S-S, relation. It's basically, he solved this in the late 18th century, I think 1792, and he gives you an explicit formula for this radius. You can see that formula in Math World. Okay, and I'm solving that cubic numerically here. But once you solve that cubic, you have this n equals 5 bicentric family. Now, what I'm also showing here are the inversive images of each one of the sidelines, these 5 blue sidelines of the original family, in this case with respect to the caustic itself. So let's invert those 5 lines with respect to the caustic. In the previous video, I had a generic circle that was concentric with I, but here I'm just going to use the caustic itself because, as we saw in the previous video, changing that radius doesn't change the topology of the phenomenon. So when you invert these 5 sidelines, you get these 5 green circular arcs, right? Because geometric inversion sends infinite lines to circles. It actually sends circles to circles, so you can think of an infinite line as being a circle of infinite radius. But since these are segments, the inversive image of each segment with respect to the circle will be a circular arc. Now, what I'm showing here on the left, and I'm verifying if the previous observation scales to n greater than 3, is both the perimeter, and I think I inverted here. L prime should have been, yeah, let's change that. Let's call this guy here L, and this guy L prime. Let's just do this online. So L is the perimeter of the bicentric family, which is known not to be conserved over the family. In fact, there's another family, which is an image of this one called the elliptic billiard or the confocal family, which conserves perimeter. But this family here does not conserve perimeter. Nevertheless, the perimeter, the sum of these arc lengths, of these 5 arc lengths, is being conserved, and that's being represented on the left there with L prime. So it's kind of neat, right? You have 5 circular arcs. By the way, they all have the same radius, and that's an obvious claim. It's easy to show that these 5 guys will have the same radii because they're all inversions of tangents to the inversion circle that are at the same radius, okay, at the same distance from the center of inversion. So each one of these guys, since the 5 sidelines of my bicentric family are at the same distance, perpendicular distance to I, their inversive image are going to be circles of the same radius. But I'm not representing here the entire circle. I'm just representing a circular arc. And the interesting phenomenon is that the total perimeter of those truncated circles, okay, is conserved, as shown here on the left. Of course, I can try this for different families by changing the relative position of I with respect to O. And when I do that, you can see here that I get a different total sum, but it's also conserved. And you get the sort of circular arc polygon of sorts. So this is kind of like a, I don't know, another view of Poncelet. Poncelet usually concerns families of polygons, and here I have a family of circular arc polygon. I don't know how much this has been studied, how trivial this is. You know, there are many interesting questions here. What's happening to the polygon of the 5 centers? Okay, what are conservations? What are characteristics of the polygon of the 5 centers? What are characteristics of the polygon of the 5 tangencies? Okay, of each one of these circular arcs, and what are characteristics of polygon of the 5 cusps, the points of incidence between these circular arcs and the inversive image of the outer circle, which is represented here by this dotted black circle. So there you have it, a conservation of the perimeter of a circular arc polygon shown here on the left. See you on the next video.